Picture, I know it doesn't make a ton of sense, but like if this were 0, you're taking a lot of these little steps, and then as soon as there's a first step that gets past x, and this is what he's calling n-1, and this first step is called n. That's all he's doing, and it makes perfect sense because that's what you would do. If I asked you find a ratio between these two numbers, this is exactly what you do. You'd be like, how far apart are they? Take a much smaller number and then just start counting until you get there. That's all he's doing, but he's doing it with an analysis group. Right? So think about it. I know these are tough, but this is just how, they're tough only because you're not used to thinking like this. And let me tell you, so maybe now I'll actually get to tell you something about this class that always, I think, scares the crap out of people. This math class is not about equality. This is not about learning when things are equal. This class is about inequality. Analysis is the study of inequality. Like, I don't know if you've noticed, but left and right, one of the first things I define is less than. I defined it abstractly as an order. And all over this proof, I'm using less than. Analysis is all about, like for instance, I'm an analyst. When I see A is equal to B, I don't see an equal sign. I see A is less than or equal to B, and B is less than or equal to A. I see the two different inequalities because that's what matters. And in analysis, it's important to show things are small, and how you show things are small. You show they're smaller than something you already know is small. Stuff like that. That's sort of the argument that happens in analysis. And that's sort of what's going on here. Is that we don't really care what that number is. We just have to show you that there's something that's below and above it that behaves how we want. Okay? I know it's hard to make jokes about inequality. Maybe never mind. It's not that important. The point is, at least as long as you're comfortable watching what I did, I'm happy. So the very last thing I want to do in class is I'm going to state the theorem I think I'm going to start with tomorrow, and then we'll move on to the complex tomorrow. But I'm not sure I'm going to prove the theorem, but what I'm going to do is I'm going to state the theorem. And 3 lemmas I think he should have written. So he assumes you knew these 3 lemmas and thought they were obvious when he did the proof. But I'm going to state the lemmas, and maybe what I will do tomorrow is prove the lemmas. I might prove the theorem, but I recommend you look at the theorem, assuming you know these 3 things. Okay. So the theorem he's asking you to prove. So remember, I started this class with Q and said, look, Q, here's 2, it doesn't have a square root. It's not in Q. Well, this is like the R's response to that problem. So theorem. So if x is a positive real number, and n is a positive integer. So I'm going to use a symbol you guys might not have seen. There exists a unique. So there exists exactly one y and r, such that y to the n is x. Yeah. Y and r, actually y positive, right? That's what's missing. This is the problem with analysis. There's all these details and I always forget them. All right, so there exists a unique positive number that is an nth root. So this is sort of the response to Q, right? Where Q didn't even have a square root for 2. Take your favorite integer, and there's that nth root for any positive number. So now if you look at the proof in Rudin, it's a bit confusing. But let me state 3 lemmas. I'm going to call this lemma 1. So I know I've been using all these different words. Proposition just means something that's nice to know. Lemma though, lemmas, the saying about lemmas is theorems don't do the work lemmas do. Lemmas are little theorems that are often easy to prove that you just cite so much. For instance, the Archimedean principle, it's a principle because it's ancient, but it would otherwise be like a lemma, right? In this case. Cauchy-Schwarz, which I'll prove tomorrow, is definitely a lemma. So I need the lemmas. So the first lemma, and I'll definitely prove the 3 lemmas tomorrow. If you have 2 real numbers, y bigger than x bigger than 0, then x to the n is less than y to the n. Right? Taking the nth power. In fact, I actually think all but the last one you guys will probably be able to prove very easily. Lemma 2. Which one's lemma 2? Right. Again, x is a real number. X is positive but less than 1. And n is greater than 1 and is an integer. Then x to the n is less than x is less than 1. I mean, again, both of these you guys should know. But these are the lemmas. So he uses these liberally within the proof and doesn't even say he uses these facts. At least the third one he mentions, but he doesn't prove it. He just says, oh, this is an obvious inequality. And so lemma 3 is, yeah. What is the condition? So if we got A, B, real numbers, n is in R, or n is an integer greater than 1, then, oh, and then I want B bigger than A, just for simplicity, everything positive. Then, if you guys can't see this, I'll rewrite it on the other board. B to the n minus A to the n is less than or equal to B minus A times n, B to the n. Or n minus 1, excuse me. Not half homogeneous. This is the weird one. This is just saying that, like, you can bound this by the difference times a high power of the bigger number. So again, this is, I know this seems weird, but these are the kind of things you do in analysis. You'll like them eventually, I hope. I mean, I'll just start showing you why these are so neat. But this is the one that he just uses this fact in his proof. And he just says, oh, this is obvious, but I want to prove this and I want to talk my way through these two groups. And that's what we'll do tomorrow, all right? So otherwise, don't forget I have office hours right after this. If you have any questions or anything, feel free to drop by office hours. Just talk to me right now, it'd be great.